Good evening, and welcome to Sleepy Gold and Silver. If you're winding down, if your eyes feel heavy, you're in the right place. Tonight's specimen is a quiet slice of Colorado vein ore that rewards patience. It is mostly pale, milky quartz, soft in the way it holds light. And then, as you look a little longer, tiny points of warm metallic yellow begin to appear across the surface. Not a loud chunk of metal, not a showy nugget, just a gentle scatter of gold, like a fine constellation that blinks on and off when you tilt the stone. The label tells us exactly what it is and where it came from. Gold with sphalerite in quartz from the Sunnyside Mine, in the Eureka District, in San Juan County, Colorado, in the United States. It measures about 8.2 centimeters by 4.9 centimeters by 0.8 centimeters, and it weighs about 59 grams. The thinness is part of its charm. It reads like a window into a vein, a cross-section through a mineralized seam, rather than a chunky hand specimen that hides its internal story. If you enjoy this slower kind of mineral talk, please like the video, subscribe to Sleepy Gold and Silver, and ring the notification bell. Tonight we're going to stay close to the specimen and to the place it came from. We will do a careful mineral tour, and we will place this piece gently on the map. First in Colorado, then in the San Juan Mountains, then in the rugged high valleys around Silverton. We will keep the pace calm and the focus steady, letting the details do the work. Now, let us begin with what you can see. This specimen is dominated by quartz, and the quartz is mostly milky white. Milky quartz is not a separate mineral from quartz. It is quartz, silicon dioxide, made cloudy by countless microscopic inclusions that scatter light. Those inclusions are often tiny fluid bubbles, minute fractures, and microscopic bits of other minerals. Instead of glassy transparency, you get a diffuse, snowy glow. In hydrothermal veins, milky quartz is extremely common because vein growth is rarely one perfect, uninterrupted crystal growth event. It is usually episodic. Cracks open, fluid flows, quartz precipitates, cracks seal, and then the cycle repeats. Each cycle leaves microtextures behind, and those microtextures soften the quartz into that milky look. Across the quartz, you can see zones that shift from white into smoky grey and darker grey. These are the sulfide-rich parts of the slice, places where ore minerals occur as fine grains, streaks, or dense patches. The label calls out sphalerite, and sphalerite is a classic mineral for this setting. Sphalerite is zinc sulfide, the most important ore mineral of zinc worldwide. In hand specimen, it can appear honey brown, reddish brown, deep brown, or nearly black. Fresh sphalerite often has a resinous luster, almost like varnished wood or dark amber. But when sphalerite is fine-grained, mixed with other sulfides, or lightly weathered, it can read as dull grey to dark grey rather than glossy brown. In a thin vein slice like this, sphalerite can be present as fine disseminations and bands, rather than as large, obvious cleavage faces. Now, the gold. On both faces of the specimen, the gold appears as countless tiny points and tiny flakes scattered through the quartz, and especially through certain sulfide-rich zones. This distribution matters. It tells you that gold was not simply poured in as one big mass. It arrived as a dispersed component of the hydrothermal system, and it deposited in specific microenvironments, along certain bands, in certain patches, in certain healed fractures. Gold in hydrothermal veins can occur as native gold, or as electrum, which is a natural gold and silver alloy. Electrum can be paler than pure gold depending on its silver content. Without laboratory work, we do not force a determination. We simply note that the label calls it gold, and visually the metal reads as warm yellow points rather than brassy sulfides. There is a simple, calming way to think about why gold looks like this in many ore specimens. Most gold in many deposits is microscopic. it can be present as tiny grains that you cannot see without magnification. Visible gold is a special moment, either because grain size is larger in that part of the vein, or because the surrounding minerals and textures make it easier for your eye to pick it out. In this specimen, the contrast helps. White quartz makes gold pop. Dark sulfide bands make gold pop in a different way, by giving it a shadowed background. The result is this quiet glitter that appears as you change the angle of the light. If you had this piece in hand, one of the most satisfying things you could do is simply rotate it slowly under a small light. Not a harsh flashlight, just a steady lamp. Gold responds with a buttery glow. It does not usually flash like a mirror. It tends to look soft and warm even when it is bright. Many brassy sulfides, by contrast, can look sharper, with more mirror-like highlights. Pyrite, for example, can sparkle in a very crisp way, and when it forms crystals, it often shows hard edges and geometric faces. Gold tends to look smoother and more rounded, even when it is crystalline. In a specimen like this, the label is our anchor, and the visual tone fits that anchor well. Now let us take a deeper mineral tour slowly and carefully, as if we are teaching our eyes what to notice. Quartz is the framework. It is hard with a Mohs hardness of 7, and it is durable. It preserves textures well. In veins, quartz can form massive milky fill, banded layers, comb textures where crystals grow inward from vein walls, and druzy surfaces where small crystals line open cavities. In this specimen, the quartz is mostly massive and milky, but there are slight changes in texture and brightness near the upper edge that hint at more open growth in places. A thin slice can capture only part of a larger story, so we describe what we see and keep our inferences gentle. Sphalerite is the zinc mineral, and it has several important properties that shape how it occurs in ore. It has excellent cleavage, meaning it can split along smooth planes. It is softer than quartz, roughly 3.5 to 4 on the Mohs scale, in a vein that can make sphalerite more prone to breakage along cleavage during mining and handling, while quartz remains more blocky and strong. Sphalerite is also chemically expressive. It is often not pure zinc sulfide. Iron commonly substitutes into its structure, and that tends to darken the mineral. Cadmium can also substitute in some systems. These substitutions can reflect the chemistry of the ore-forming fluids and the conditions under which sphalerite grew. In the broader Eureka District and the Silverton area, veins can carry a whole suite of sulfide and sulfur salt minerals. Common companions in many polymetallic epithermal veins include galena, which is lead sulfide and often shows a bright lead-grey colour and cubic cleavage, chalcopyrite, a brassy copper-iron sulfide, and pyrite, iron sulfide, often pale brassy and sometimes crystalline. Silver can occur as native silver, as silver sulfides, and as silver-bearing sulfur salts in some districts. Carbonate minerals can also be present in some San Juan veins, and the district is famous among collectors for certain carbonate and sulfide assemblages. But for this specific specimen, our named mineral trio is simple and strong: quartz, sphalerite, and gold. There is another subtle point here that collectors learn over time. The way minerals share space can be just as important as which minerals are present. A thin slice like this can show the relationship between gangway and ore, between the silica framework and the metal-bearing zones. In many systems, the metal-bearing minerals are not evenly distributed. They can concentrate along certain layers or certain microfractures. When you see gold sprinkled more densely near darker zones, it suggests that gold deposition was linked to the same stages that deposited sulfides, or that sulfide-rich zones provided the surfaces and microenvironments that helped gold drop out of solution. Sometimes gold is truly enclosed in sulfides as microscopic inclusions. Sometimes it is attached to sulfide grains. Sometimes it sits in tiny fractures that cut through both quartz and sulfides. Without microscopes, we do not claim a specific mode for this specimen, but the overall pattern, gold points scattered through quartz and near sulfide zones, is classic for many hydrothermal vein ores. Now let us talk about what kind of specimen this is, because specimen style influences how we experience it. This is essentially a vein slice, a thin piece that likely broke along or across a mineralized seam. It is not a polished slab with a glossy surface that exaggerates color and pattern. It looks more like a natural fragment, and that natural surface is valuable. It preserves real textures rather than polishing them into abstraction. The thickness, about 0.8 centimeters, makes it light and easy to handle, but still thick enough to feel like a real piece of ore rather than a wafer. It is the kind of piece you could hold between thumb and finger and rotate slowly without fatigue, and it would keep giving you small changes in appearance as the gold catches light in new angles. From the standpoint of collecting, it is also a very honest specimen. It teaches you what ore can look like when the gold is present but not screaming. It is not a theatrical piece. It is representative. It is a window into a working mine system where gold and base metal sulfides were part of the same economic story. Now that we have stayed close to the specimen, let us place it gently on the map. We are in southwestern Colorado in the San Juan Mountains. The San Juan Mountains are among the most rugged and dramatic ranges in the Rocky Mountains, and they are famous for being volcanic at their core. This is not a range built mostly from ancient granites and metamorphic rocks. This is a range built from a thick pile of volcanic rocks, lavas, volcanic breccias, and ashflow tuffs, erupted in a long and complex volcanic history. Later, uplift and erosion carved the volcanic pile into high peaks and deep valleys, and repeated glaciations sculpted the landscape into cirques, sharp ridges, and steep-walled canyons. The town most closely tied to our specimen is Silverton. Silverton sits in a high mountain valley, historically a mining town and still surrounded by clear evidence of volcanic geology and hydrothermal alteration. Nearby are old mining camps and districts, places like Eureka and Animus Forks, that once held mills, tunnels, tramways, and winter stories. San Juan County, where Silverton sits, is high country in every sense. The air is thin, the winters are long, the terrain is steep, and that ruggedness is part of why the mining history here is so involved. Every ton of ore moved in the early years was long, steady work shaped by distance and weather. The Eureka District sits near Silverton, and the Sunnyside Mine is one of the major mines of that district. The mine and the district are tied to a structural feature called the Eureka graben. A graben is a downdropped block of crust bounded by faults, formed when the crust is pulled apart. You can imagine it as a long, fault-bounded trough. What matters for mineral deposits is that grabens and fault corridors create fracture networks. Fracture networks create permeability. Permeability is what hydrothermal fluids need. Hot water, carrying dissolved silica and metals, rises along these structures. When conditions change, minerals precipitate, and over time those structures become veins. If you like to picture geography as a slow flyover, imagine starting far above the western United States and easing toward the southern Rocky Mountains, then drift toward southwestern Colorado, where the San Juan Mountains rise like a stormy frozen sea of ridgelines. As you descend, you begin to see the branching valleys carved by rivers and ice. The Animas River drainage is one of the key drainages in the Silverton region, a mountain river system that helped cut into the volcanic pile and expose the geology. Tributary valleys and gulches run into the main valley, and many of the old mine sites sit up these side valleys, where veins were accessible in steep slopes. Now there is another regional phrase that helps situate Silverton geologically: the Colorado Mineral Belt. The Silverton caldera area lies near the southwest end of that belt, a broad regional trend of igneous activity and mineral deposits across Colorado. You do not need that phrase to appreciate the specimen, but it helps you remember that this district is not isolated. It is part of a larger pattern of magmatism and mineralization in Colorado. with many famous districts tied to igneous intrusions and hydrothermal systems. Staying with the immediate area, the word caldera appears again and again in San Juan geology. A caldera is a large volcanic subsidence feature formed when a huge eruption empties a magma reservoir and the overlying ground drops down. Calderas can be many kilometers across. They create ring faults and extensive fracturing. They can later experience resurgence, where the caldera floor domes upward. Calderas can also be nested, forming new calderas inside older calderas. The Silverton area is a place where caldera history is layered and complex, and that complexity is directly tied to the structural plumbing that guided hydrothermal systems. We're not going to dive into all the caldera mechanics yet. That will come in the geologic setting portion, but even here in the geographic setting, it helps to understand why the district is so mineral rich. Volcanoes did not only build the mountains, they broke the crust repeatedly. They created fault corridors and ring fractures. Those structures became highways for hot fluids, and hot fluids are the artists that paint quartz, sulfides and gold into cracks. Now let us bring the focus back to the specimen's locality name, because locality names carry a kind of layered meaning. Sunnyside Mine is not only a place name, it is a clue to the scale and maturity of mining in this district. Mines that became widely known often did so because they had extensive workings and sustained production. A mine like Sunnyside is tied to the evolution of ore processing, as well as to ore discovery. And a district like Eureka is tied to a landscape where many veins were explored, but only certain structures and certain chutes produced reliably enough to become major operations. In practical collecting terms, Sunnyside Mine, Eureka District near Silverton, is a provenance that immediately places a specimen in one of the classic volcanic-hosted mining regions of the United States. It tells you to expect polymetallic veins, to expect quartz and sulfides, to expect a hydrothermal story shaped by faults and calderas. Now let's go even deeper into mineralogy, because mineralogy is the language that will carry us through all three parts of this longer narration. Start with quartz again, and consider what quartz is doing in a vein. Quartz is deposited when silica-rich fluid becomes supersaturated with respect to quartz. Supersaturation can happen through cooling, through boiling, through pressure changes, and through chemical reactions. When a fluid boils, for example, it can lose some volatile components and change its ability to dissolve silica. When pressure drops, the solubility of silica can change. When fluids mix, chemistry can shift. Quartz precipitation is often the backbone of hydrothermal mineralization, because silica is abundant and because quartz is stable over a wide range of conditions. In veins, quartz can grow in different habits. Comb quartz is one, where crystals grow inward like teeth. Crustiform banding is another, where layers build like fine stripes. Massive milky quartz is common when the vein fills quickly or repeatedly with fine-grained quartz. In this specimen, the overall feel is massive with subtle layering, which is consistent with repeated pulses of quartz deposition that were not always perfectly open-space crystal growth. Now consider sphalerite and why it appears where it does. Sphalerite precipitates when zinc in solution meets conditions where zinc sulfide becomes stable. That stability depends on sulfur availability, temperature, and the overall chemistry of the fluid, including things like acidity and oxidation state. In many polymetallic systems, zinc and lead can travel in hydrothermal fluids and then precipitate as sphalerite and galena when conditions shift. Those shifts can be driven by boiling, mixing, cooling, or reactions with wall rock. Sphalerite can form in bands, in patches, as fine disseminations, or as more massive zones. It can also show subtle zoning in composition, especially in iron content, reflecting changes in fluid chemistry during growth. Again, without lab work, we do not assign a specific composition here. But the presence of sphalerite tells us we are in a base metal-bearing vein environment, rather than a purely gold quartz vein environment. Now consider gold, and how gold moves through the earth. Gold is not very soluble in plain water under surface conditions. In hydrothermal fluids, gold can be transported as complexes, often involving sulfur species. The exact chemistry can be complex, but the broad idea is simple. In hot chemically active fluids, gold can travel invisibly in solution. Then, when conditions change, gold can become unstable in solution and precipitate as native gold or as gold-silver alloy. One of the most effective triggers for gold deposition in shallow hydrothermal environments is boiling. Boiling changes fluid chemistry. It can cause sulfur species to partition into vapor. It can change acidity. It can change oxidation state. Those changes can sharply reduce gold solubility, causing gold to precipitate. Another effective trigger is rapid pressure drop during fault movement, which can drive abrupt phase separation and strong chemical shifts. Another is mixing of fluids with different chemistry, which can destabilize dissolved complexes. Another is reaction with wall rock or with precipitating sulfides, which can consume sulfur species and change the fluid's ability to hold gold. In a specimen like this, you do not need to choose one trigger. You can simply recognize that the distribution of gold points suggests gold was deposited during specific moments and in specific microspaces rather than being uniformly spread. Now let us take a calm tour of what you might reasonably expect in the broader mine environment, while staying honest about what this specimen specifically shows. In many polymetallic veins in volcanic regions, you can see sequences of minerals that reflect evolving fluid conditions. Early stages can be dominated by quartz and iron sulfides like pyrite. Later stages can introduce lead and zinc sulfides like galena and sphalerite. Copper sulfides like chalcopyrite can appear. Silver-bearing minerals can appear in several forms. Carbonates can appear as late-stage gangue minerals in some systems. Sometimes veins show open-space textures like vugs lined with quartz, or banding that looks almost like tree rings, or breccias where fragments are cemented by later quartz and sulfides. Some of these textures are subtle in our thin slice, but the general vein environment that produces quartz plus sphalerite plus gold is part of that family of textures and sequences. The educational value of the specimen is that it sits right in the center of that story. It is not a weird outlier. It is a clean example of a common association: precious metal plus base metal sulfide in vein quartz. Now let us bring the geography and the mineralogy together with a little imagined field moment, because that often helps the mind settle. Imagine you're in the Silverton area on a cool summer day. The sky is high, clouds build over the ridges, the air smells like wet stone and alpine plants. You're walking on a steep slope of volcanic rock and talus. Above you are rust-stained outcrops where altered rock weathers into oranges and reds. Below you, a valley drops toward the river, and in the rock under your boots there are fractures, faults and joints that cut the volcanic pile. In some of those fractures, milky quartz fills the cracks. In some of those quartz seams, darker sulfides appear in streaks and patches, and occasionally, in the right seam, gold occurs as tiny grains, so fine you would miss it unless you knew how to look. That is a realistic way to imagine the setting. It is not romantic, it is practical. The district is steep, fractured, altered and mineralized. The ore is in veins. The veins are controlled by structure, and the minerals in the veins reflect the chemistry and physics of the hydrothermal system that once circulated through those fractures. Now, because this is a sleep channel, I want to keep the rhythm steady and soothing. So we will do one more gentle pass over the specimen itself, but with new angles of attention rather than repeating the same words. Look first at the lightest quartz zones. These zones show the quiet continuity of silica deposition. They are not chaotic. They feel like a stable background. Then let your eyes drift toward the smoky zones. These areas show where the vein chemistry or the vein openings favoured sulfide deposition. The grey is not a single uniform sheet. It is mottled, layered, and patchy, suggesting that sulfides were deposited in pulses and perhaps along microfractures and grain boundaries. Now let your attention fall on the gold points. They are small enough that you imagine them as grains rather than masses. Their small size is itself a lesson. Gold in ore is often subtle. The way the gold is scattered suggests that gold was present in the fluid and deposited repeatedly, perhaps in association with multiple pulses rather than in one late-stage event. The gold points are numerous, and that matters for the visual impression. A single grain can be dismissed as accidental. A field of grains has to be explained by the system. This is also where the thinness of the specimen helps. In a thick chunk, gold might be hidden inside and only appear on a fresh break. In a slice, the surface area is large relative to thickness, so you see more of the internal distribution. That makes this kind of piece excellent for teaching and for calm contemplation. Now, before we drift deeper, I want to give you a clean, simple summary of where we are, because that will make the transition into the geologic setting feel effortless later on. We have a labelled specimen from the Sunnyside Mine in the Eureka District near Silverton in the San Juan Mountains of Colorado. The specimen is quartz-rich, with sphalerite as a key sulfide mineral and visible gold dispersed as tiny points and flakes. The specimen style is a thin vein slice which highlights relationships between gangue and ore minerals and suggests a multi-pulse vein history. The geographic setting is a rugged volcanic mountain range shaped by caldera volcanism, faulting hydrothermal alteration, and later erosion and glaciation. Even without diving into the deeper mechanics yet, the setting already points toward a hydrothermal vein system guided by major structures like the Eureka graben. With that foundation in place, we can gently open the door into the deeper geologic story, the volcanic history of the San Juan region, the caldera complex near Silverton, and the quiet processes that can turn hot water into quartz veins, sulfide bands, and finally gold. Let us begin by returning gently to the San Juan Mountains as a geologic machine. The San Juan Mountains are volcanic at heart. That single fact explains so much. Volcanic mountains are not just piles of lava flows. They are layered archives of eruptions, lavas, ash deposits, welded tuffs, breccias, volcanic sediments, and intrusions that cut through them. When you stand near Silverton, you're standing on the remains of a very large volcanic field, built over millions of years by repeated eruptive phases, and then reshaped by collapse, uplift, and erosion. In many volcanic fields, the story moves from smaller eruptions to larger ones, and then into caldera-forming events. A caldera is not a simple crater. It is a collapse structure formed when an enormous eruption evacuates a shallow magma reservoir and the roof drops in. That collapse produces ring fractures and ring faults, and it fractures rock over a huge area. Then, after collapse, the system often resurges. The caldera floor can dome upward again as magma refills the system or intrusions push upward. That uplift stretches the rock, and stretching creates new faults and fractures. And then, as the system cools, hydrothermal circulation can intensify, hot fluids moving through the newly fractured crust. If you keep only one mental picture for tonight, make it this. Calderas break the crust on a grand scale, and hydrothermal systems use those breaks as pathways. Ore deposits are, in a very literal way, mineralized pathways. Now, the Silverton area sits in a particularly complex caldera setting, with nested and overlapping structures. There are older, larger calderas in the western San Juan region, and later caldera activity overprints them. This matters because nested structures create intersections, ring fractures crossing earlier faults, grabens crossing caldera margins, and new fracture sets cutting old ones. Intersections are where permeability tends to concentrate, and permeability is the doorway for fluid flow. The Eureka graben, which is so closely tied to the mining district and the Sunnyside Mine, is an example of a structural corridor that is favourable for repeated movement and repeated fluid access. A graben is a down-dropped block bounded by faults formed in extension. In volcanic and caldera terrains, extension can occur during resurgence when the ground domes upward and stretches, cracking along the crest. In plain language, the ground rises, it pulls apart, and the faults create a long, broken corridor. That corridor can remain active, opening in small events over and over, which means it can remain permeable for a long time. Now let us bring our specimen back into the frame while we talk about structures. A quartz vein is, at its core, a fracture that got filled. It might have been a fault plane. It might have been a dense network of small fractures near a fault. It might have been a crack opened by a small slip event. Whatever the exact geometry, the crucial thing is that it opened at least briefly, and then it was fed by mineralizing fluid. The specimen we have is thin, like a slice. That thinness is helpful because it hints at the way veins grow. If veins formed as one slow, continuous filling event, you would expect more uniformity. But many veins are layered, patchy, and banded because they formed in pulses. And pulses in the earth often mean stress events. A fault moves, a crack opens, fluid rushes in, minerals precipitate, the crack seals. Then, later, another movement event opens it again. This repeated opening and sealing is one of the most elegant processes in geology, and it is also one of the most calming to think about because it is rhythmic. It is not chaos. It is a pattern repeated over time, recorded in mineral layers. Now we can talk about the volcanic pile itself. What kinds of rocks are hosting the veins, and why those rocks matter. Volcanic terrains are mechanically diverse. A dense lava flow fractures differently than a porous ash deposit. A welded tuff can be tough and brittle, creating sharp fractures that can stay open long enough for open space quartz growth. A non-welded tuff can be weaker and more ductile, crushing and sealing in a different way. Volcanic breccias can be intensely fractured and permeable. Intrusions can bake and harden adjacent rock, changing fracture behaviour. All of these contrasts influence where veins form and how they evolve. If you imagine a hydrothermal fluid rising through this pile, it will not move evenly. It will prefer certain horizons and certain structures. It will exploit faults and fracture networks. It will pool, move, and sometimes become trapped behind sealed segments. When trapped fluids build pressure, the next opening event can be more dramatic. That is how you can get hydrothermal breccias, broken fragments cemented by quartz and sulfides when pressure is released quickly in rock fractures. Even when you do not see a dramatic breccia texture in a specimen, the same physics can still be present at smaller scale, microfracturing, rapid sealing, and repeated pulses. Now we move from structural pathways to the hydrothermal fluids themselves. Hydrothermal fluid is mostly water, but it is not plain water. It is water that has been heated, pressurized, and chemically enriched by interaction with rock, and often by input from magmatic gases and fluids. In volcanic settings, there are typically two broad fluid sources that mix to varying degrees: meteoric water, which is rain, and snowmelt circulating down and back up, and magmatic fluid, which is fluid and gas released from cooling magma. The mix matters. Meteoric water tends to be more dilute. Magmatic contributions can bring acidity, sulfur, chlorine, carbon dioxide, and metal transport capacity. As these fluids move, they react with wall rocks. They exchange ions. They dissolve silica and mobilize metals. The fluids become, in a sense, liquid geology, carrying the ingredients for new minerals. But fluids do not deposit minerals just because they are carrying them. Something has to change. There must be a trigger that causes the fluid to become supersaturated with respect to a mineral, or that destabilizes a dissolved metal complex. In epithermal vein systems, the most important triggers tend to be pressure drop, boiling, cooling, and mixing. And among these, boiling is often the star. Boiling in hydrothermal systems is not just a physical change. It is a chemical event. When a fluid boils, it separates into a vapor phase and a liquid phase. Certain gases preferentially partition into the vapor, especially species like hydrogen sulfide and carbon dioxide. As those gases leave the liquid, the chemistry of the remaining liquid changes. Acidity can shift. Oxidation state can shift. Sulfur chemistry can shift. And those shifts can strongly affect the solubility of metals, including gold. Gold transport in hydrothermal fluids is commonly explained by sulfur complexes. In hot sulfur-bearing fluids, gold can be carried as dissolved complexes, especially involving bisulfide species. You can think of this as the fluid holding gold in an invisible chemical grip. If boiling removes sulfur species from the liquid, or changes the conditions that stabilize those complexes, the grip loosens. Gold becomes unstable in solution. It precipitates as native gold or as a gold-silver alloy. This is one reason why visible gold in epithermal environments is often associated with vein textures that imply boiling and rapid pressure change. Banded quartz, open space textures, and zones of repeated fracturing. Now let us bring sphalerite into the fluid story. Sphalerite is zinc sulfide, so its precipitation requires zinc in solution, and sulfur availability under conditions where zinc sulfide becomes stable. Zinc can be transported in chloride complexes and other forms in hydrothermal fluids. The stability of sphalerite depends on temperature, sulfur activity, and the broader chemical environment. In intermediate sulfidation systems, base metal sulfides like sphalerite and galena are common, reflecting fluid conditions that favour substantial sulfide deposition, while not being as extremely acidic and oxidized as high sulfidation systems. The phrase sulfidation state comes into play here. Sulfidation state is a conceptual measure of how sulfur-rich and chemically sulfide-friendly a fluid environment is, and it influences which sulfide minerals are stable. Intermediate sulfidation deposits often host assemblages that include sphalerite, galena, chalcopyrite, pyrite, and a range of silver-sulfur salts. The exact suite can vary from district to district, but sphalerite is a very comfortable resident of that middle ground. And here is a subtle point that ties gold and sphalerite together. Gold deposition can be promoted when sulfide minerals precipitate, because sulfide precipitation consumes sulfur species from the fluid. When sulfur species are consumed, gold-sulfur complexes can become less stable. That can push gold out of solution. So in some systems, the same chemical evolution that promotes base metal sulfide deposition can also encourage gold deposition, especially when combined with boiling and pressure drop. This is why gold and base metal sulfides can be intimately associated, and why a specimen labelled gold with sphalerite and quartz is such a clean, educational snapshot of a larger geochemical story. Now let's talk about the texture of quartz itself, because quartz is not just a filler. Quartz is the record keeper. Quartz precipitation can happen under a range of conditions, and the texture of quartz reflects those conditions. Massive milky quartz can indicate rapid deposition, repeated deposition, or extensive microfracturing and inclusions. Banding can indicate repeated pulses and changes in fluid chemistry. Comb quartz, crystals growing inward from the walls, indicates open space and steady growth into a void. Druzy quartz indicates open cavities where fluid could circulate late. Breccia cement indicates episodes where rock broke and was then healed by new quartz. Our specimen shows mostly milky quartz with subtle banding and sulfide-rich zones that suggest pulses rather than one uniform event. The gold specks appear distributed in a way that also implies episodes. Certain bands and patches are more favourable. Now let us take a slow, deeper dive into alteration, because alteration is the halo that surrounds veins and tells you what the fluid did to the rock. Hydrothermal alteration is essentially chemical weathering at depth, driven by hot fluid rather than cold rainwater. When hydrothermal fluid flows through volcanic rock, it can transform the mineralogy. Feldspars can turn into clays. Mafic minerals can transform into chlorite. Glassy volcanic material can devitrify and alter. Sulfur-bearing fluids can introduce sulfides. Silica can flood the rock, hardening it. In some cases, rocks become so altered that they lose most of their original mineral identity. In volcanic hydrothermal systems, there are common alteration styles that geologists use as a language. Propylitic alteration often includes chlorite, epidote, calcite, and sometimes pyrite. It tends to form in outer zones where fluids are cooler or more reacted. It often gives rocks greenish tones and a certain toughness. Sericitic alteration involves fine white mica, often called sericite, along with quartz and commonly pyrite. It can reflect more intense alteration, often at higher temperatures or in zones of strong fluid flow. Argillic alteration involves clay minerals, kaolinite, illite, smectite, and others, and often forms when fluids are relatively acidic or when feldspars are altered into clays. These rocks can become soft, friable, and unstable. Advanced argillic alteration involves minerals like alunite and pyrophyllite, and is characteristic of more strongly acidic, oxidized conditions, often associated with high sulfidation systems and shallow lithocaps. In the broader Silverton area, altered rocks are widespread, and modern studies have used geophysical methods to map altered zones, because alteration changes rock properties like magnetization and electrical resistivity. That is part of the modern way of seeing ore systems, not only mapping veins at the surface, but imaging the broader alteration footprint that indicates a hydrothermal center. Now, how does alteration connect to our specimen? Even though our specimen is mostly vein material, the alteration story still matters because alteration changes permeability. Altered rocks can be weaker and more fractured. They can channel fluids. They can respond differently to stress. They can also interact chemically with the fluid, changing fluid composition and promoting mineral precipitation. In many ore systems, alteration and mineralization are partners. Fluid flows, rock changes, and the change rock guides fluid flow even more effectively. Now we can talk about depth, because depth controls pressure and pressure controls boiling. In epithermal systems, there is a depth range where boiling is most effective. At shallow enough depths, pressure is low enough that fluids can boil at the temperatures typical of hydrothermal systems. If the system is too deep, boiling may be suppressed because pressure is too high. If the system is too shallow, fluids may cool too quickly, or the system may become dominated by vapor and acidic steam-heated alteration rather than metal deposition. Many epithermal veins form in a sweet spot where fluids are hot enough to carry metals, and pressure drops are sufficient to induce boiling and rapid chemical changes. The Sunnyside system, being a vein deposit in a volcanic caldera setting, fits very well into that conceptual framework. Veins extend through significant vertical ranges, and different levels can show different textures and mineral assemblages. That vertical complexity is one reason districts like this can produce diverse specimens, and why mines can chase veins for long distances and depth ranges. Now, let us bring in the concept of ore chutes, but in a geology-first way. An ore chute is a zone of higher grade or thicker vein. Chutes often form where the fracture system created more open space, or where repeated reopening focused fluid flow. In fault-controlled veins, bends, jogs, step-overs, and intersections are classic chute-forming locations. In caldera terrains, intersections between ring fractures and graben faults can be especially favourable. If you have two fracture sets crossing, you often have enhanced permeability, and you have geometry that can create dilation during movement. Dilation means open space. Open space is where quartz and sulfides can grow effectively, and where boiling and pressure drop can occur in a physically meaningful way. If you look at our specimen and see that the sulfide-rich and gold-rich zones are not uniform, that unevenness is a tiny echo of chute behaviour. even within a small fragment, mineralization intensity varies. That is not random. It reflects the underlying physics and chemistry of how fluid moved and where it dropped its load. Now, let us do a slow, coherent walk through the likely sequence of events that could produce a piece like this, keeping it calm and continuous. First, volcanic rocks are built, lavas and tuffs stacked thick in the San Juan volcanic field. Calderas collapse and fracture the crust. Later resurgence and continued tectonic and volcanic adjustments create fault corridors, including extensional structures like grabens and associated fracture networks. Second, intrusions at depth provide heat and potentially magmatic fluids and gases. Meteoric water circulates down, heats, reacts with rock, and rises. The system becomes a hydrothermal convection cell powered by heat and guided by structures. Third, fluids rise along fault zones. At certain levels, pressure drops allow boiling or phase separation. Silica becomes supersaturated and quartz precipitates. Early quartz may line fracture walls and begin to seal openings. Iron sulfides like pyrite may also precipitate early as the system establishes sulfide stability. Fourth, as the system evolves, base metals become prominent in the fluid. Zinc and lead precipitate as sphalerite and galena in zones where sulfur activity and temperature favour them. These sulfides can occur as bands, patches and disseminations within the quartz. The vein darkens in those zones. Fifth, gold carried in solution becomes unstable during specific events: boiling, rapid pressure drops, mixing, or sulfidation reactions. Gold precipitates as fine grains and flakes, often attached to or near sulfides and within microfractures in quartz. The distribution becomes speckled rather than massive. Sixth, the fracture seals, and later movement reopens it, producing new microfractures that cut existing material. New quartz precipitates, sealing those fractures and sometimes introducing subtle banding and healed textures. Over time, the vein becomes a composite archive. Now this is the part I really like, because it connects the physics of the Earth to a tactile, quiet reality. Think about how many times a fracture has to open for a vein to become thick and mineralized. Not once, many times. Think about how many chemical changes have to occur for quartz, sphalerite, and gold to deposit in the same piece. The system must shift between silica saturation, sulfide stability, and gold precipitation conditions. That shifting is the heartbeat of hydrothermal ore formation, and it is why ore minerals often appear in stages and bands. The specimen, even without dramatic crystals, carries that staged history. The milky quartz is the background rhythm of silica deposition. The grey sulfide bands are the base metal pulses. The gold specks are the precious metal moments that occurred when conditions aligned. Now, let us add one more layer: why the quartz is milky, and why that is actually useful. Milky quartz often contains abundant fluid inclusions, even if you cannot see them. Fluid inclusions are tiny pockets of fluid trapped during crystal growth. Under a microscope, fluid inclusions can reveal temperature and fluid composition, and they can show evidence of boiling when inclusions capture both liquid-rich and vapor-rich forms. We are not doing lab work tonight, but the concept helps you appreciate that milky quartz can be a physical archive of hydrothermal fluid behavior. The cloudiness is not just cosmetic, it can be the signature of a complex growth environment. Now, let us talk about the broader deposit classification landscape, because this helps anchor Sunnyside without forcing it to carry every detail. Epithermal deposits are often grouped into low sulfidation, intermediate sulfidation, and high sulfidation families. Low sulfidation deposits often form from near-neutral fluids, can show strong quartz adularia banding, and can host gold and silver with relatively lower base metal content in some cases, though there are exceptions. High sulfidation deposits often involve acidic, oxidized fluids derived from magmatic gases, producing advanced argillic alteration and distinctive minerals like alunite. Intermediate sulfidation deposits often sit between these extremes, with abundant base metal sulfides, silver sulfur salts, and gold, and often with strong structural control by veins in volcanic terrains. Sunnyside is often discussed in that intermediate space, a polymetallic vein system with significant base metals and precious metals, structurally controlled in a caldera-related fault corridor. What that means for your specimen is straightforward and satisfying. Gold is present, but it is part of a wider metal story. Sphalerite is not a strange extra, it is a central component. Quartz is the dominant gangue consistent with epithermal vein formation, and the subtle banding and zonation fit the idea of multi-stage hydrothermal deposition. Now let's do a gentle mental experiment, because it helps connect boiling and mineral deposition to something intuitive. Imagine you have a sealed bottle of carbonated water. Under pressure, carbon dioxide stays dissolved. When you open the bottle, pressure drops, and gas comes out of solution quickly, forming bubbles. Hydrothermal boiling is not exactly the same, but the analogy is useful. Pressure drop forces a dissolved component to separate into a gas phase. That separation changes the chemistry of the remaining liquid. Now imagine that in the hydrothermal fluid, sulfur-bearing gases and carbon dioxide behave in a similar way during boiling. When those gases leave the liquid's chemistry changes. Metals that were stable as dissolved complexes can become unstable. Minerals can precipitate. In other words, pressure drop is not just a mechanical event. It is a chemical lever. Fault movement and fracture opening can pull that lever repeatedly, and each pull can deposit a thin layer of quartz, a band of sulfides, or a dusting of gold. Now, to keep this tied to the specimen rather than drifting too far into abstraction, let us return to what you can actually see in the photos. The specimen shows a pale quartz field with darker zones that appear as bands and patches, and the gold is more apparent in certain areas. That visual pattern is exactly what you would expect if mineralization was pulsed and chemically zoned at small scale. A uniform chemical bath does not produce this. Repeated events do, and that is, to me, the most satisfying geologic takeaway. This piece is a record of repeated events, captured in stillness. Now we can let the human story settle in, and we can do it with one final geologic bridge. Why a mine like Sunnyside could be large and long-lived in a setting like this. Large, long-lived vein mines require a combination of factors: persistent structures, persistent fluid flow, sufficient metal supply, and enough repeated opening to keep pathways active. Calderas and graben fault corridors are excellent at providing persistent structures. Volcanic centers provide heat. Magmatic and meteoric fluid systems can provide sustained circulation. And repeated fault movement can provide repeated openings. When those factors align, veins can be extensive, traceable, and miniable over long distances and vertical ranges. That, in a calm nutshell, is why a slice of gold with sphalerite and quartz can come from a mine with real industrial history. The geology supports scale. So take a slow breath here. Let the image of the veins settle again. A fractured volcanic mountain, hot water rising, pressure dropping, quartz sealing, sulfides banding, and gold quietly appearing as tiny grains. From that quiet framework, we can drift into the human story, how the Eureka District and the Sunnyside Mine fit into the wider history of the Silverton area, and how technology changed what could be mined. So let us begin the history where the landscape begins for humans, with use and access and what changed. For a very long time, the San Juan Mountains were a seasonal homeland and hunting ground for the Ute people who moved through this high country with deep knowledge of weather, terrain, and wildlife. In the mid-19th century, as prospectors and survey parties pushed into the interior west, the mineral potential of the San Juan region became increasingly obvious to outsiders. Some early prospecting happened even before formal access was granted, And then, in the year 1873, the Bruneau Agreement opened a large portion of the San Juan region to mining and settlement by the United States, while also reserving certain rights for the Ute people, including the right to hunt in the area under specified conditions. That agreement is one of the turning points you can almost feel in the landscape history of Silverton. It is the moment when mineral rumours could turn into camps, claims, and permanent infrastructure. Not long after that, mining camps began to appear in the high valleys. The geography matters here. Around present-day Silverton, the valley known historically as Baker's Park became a focal point because it offered a place to build in a rugged setting, and because the surrounding slopes and tributary gulches led directly toward mineralized structures. Silverton itself was established in the year 1874, and it quickly became a hub for nearby camps such as Howardsville and Eureka. When you read those names on old maps, it helps to remember that these were not separate worlds. They were linked points in one steep, high-elevation mining network connected by trails, wagon roads, and later rail lines. Eureka in particular is tightly bound to the Sunnyside story. The Sunnyside Mine sits in the Eureka District, and the district is defined by the structural corridor we have talked about, including the Eureka graben and its associated fault and fracture network. In plain terms, the geology created a long-lived set of cracks that were good at being filled, reopened, and filled again. The human settlement pattern followed that same logic. Camps formed where veins could be worked, where timber and water were available, and where ore could be moved out of steep terrain. In the earliest years, mining in the San Juan region faced a challenging balance. The ore could be rich, but the environment was costly. High elevation means short construction seasons. Heavy snow means long periods when travel is slow or uncertain. Steep slopes mean that hauling and building are never simple. In the earliest phase of many Western camps, only the richest, most easily shipped ore could pay. That tends to favour hand-sorted material with high grades, because you cannot afford to move waste. This is why early mining narratives often emphasise spectacular pockets, unusually rich streaks, and shipments of select ore. But the districts that last are usually the ones that transition from a pocket economy to an infrastructure economy. They go from carry out what you can to build a system. And in Silverton and Eureka, transportation became the hinge. A major milestone came in the year 1882, when the Denver and Rio Grande rail line reached Silverton from Durango, allowing heavy freight and ore to move far more efficiently than by wagon alone. When a rail connection arrives in a steep mining district, it changes everything. The cost of supplies drops, the cost of shipping ore drops, and the possibility of building larger mills and concentrating plants becomes realistic. It also changes what kinds of ore can be mined profitably, because complex ore often needs treatment at scale. And complex ore is the key phrase for the Eureka District. The veins of the district are often polymetallic. That means they can contain valuable mixtures of metals in the same ore: silver, lead, zinc, copper, and gold. From a collector's standpoint, polymetallic ore is exciting because it can be mineralogically diverse. From an operator's standpoint, polymetallic ore can be frustrating because you have to separate minerals that are physically and chemically tangled together. This is where the Sunnyside Mine becomes more than a mine name. Sunnyside becomes a symbol of metallurgical progress. In the late 19th century, as many districts matured, ore treatment improved. Concentration methods, roasting methods, and smelting logistics gradually expanded what could be processed economically. But the major leap for many lead and zinc districts came with flotation, especially selective flotation. Flotation is a deceptively simple idea with deep practical power. You crush and grind ore until mineral grains are liberated from each other. Then you put the powdered ore into water with carefully chosen reagents. Those reagents cause certain mineral grains to become water repellent, so they prefer to attach to rising air bubbles. When air is introduced, bubbles rise, and the targeted minerals ride those bubbles upward into a froth layer that can be skimmed off. With the right chemistry, you can float one mineral first, then another, producing separate concentrates instead of one mixed, hard-to-smelt product. In the year 1917, the first commercial lead-zinc selective flotation plant in North America was introduced at the Sunnyside Mine. That is an astonishing point in industrial history, and it fits the specimen in your hand perfectly, because your specimen is literally gold with sphalerite and quartz. Sphalerite is zinc sulfide. Zinc ores are exactly the kind of material that selective flotation can make profitable at scale, especially when they occur with lead, iron sulfides, and precious metals. In other words, the mineral association you see in the slice is not only geologically meaningful, it is historically meaningful. It is the kind of ore that pushed technology forward. Now let us stay with the mine history itself, but keep the tone slow and steady, because the point here is not to race through a timeline. The point is to let the story deepen the way a vein deepens by quiet accumulation. Mining activity in the Eureka District fluctuated with metal prices and broader economic cycles. Silver, in particular, was vulnerable to price shifts and policy changes, and major silver price collapses in the early 1990s of the 19th century affected mining activity across the West. When silver prices fall, marginal operations stop first, and even good mines can be forced to change their plans. Districts with complex ores often survive these cycles by leaning on improved processing and by shifting which metals are emphasized as markets change. Through the 20th century, mines in the Silverton region continued in various forms, sometimes intensifying, sometimes pausing, often responding to the shifting economics of metals and the evolving ability to treat complex ore. One of the reasons Sunnyside remained notable is that it was not only a vein system with valuable minerals, it was also a mine with infrastructure and technical capacity, able to work ores that were not simple. That brings us to a quiet but fascinating detail that connects directly back to the gold you can see in your specimen. In the year 1971, ores with visible gold at Sunnyside were rediscovered in a way that drew scientific attention, because they offered an opportunity to study gold occurrence in relatively young, unoxidized fissure vein ore. In the mid-1970s, the mine was described as a major producer of gold-silver base metal ore, and one published account noted that it was Colorado's leading gold producer in the year 1974, with reported gold production on the order of tens of thousands of ounces. That is not a claim we need for collecting, but it is a powerful reminder that visible gold in a vein slice is not only a collector's delight, it reflects real ore that mattered economically and scientifically. If you have ever wondered why certain mines become so studied, it is often because they offer something rare: clarity. Unoxidized ore preserves original mineral relationships. Visible gold makes those relationships easier to map, and when you combine those two, you get a natural laboratory. A thin slice of gold-bearing quartz becomes more than a display item. It becomes a teaching tool for how gold sits in a hydrothermal system. Now we can shift into one of the most dramatic but also most geologically instructive events in the Sunnyside story, and I will tell it in the calmest possible way, because it is, at its core, a story about water and rock. In the late 1970s, an event involving Lake Emma and underground workings became widely known. Lake Emma is a small high-elevation lake in the Sunnyside area. In the year 1978, the lake drained into the mine through an opening that connected the lake to underground openings, sending a rapid flow of water and sediment through the workings and out through drainage pathways. The details can be complex, but the basic lesson is simple and deeply geological. In high mountain terrain, water, rock, and mining voids can interact in powerful ways. Glacially carved basins can sit above fractured rock. Underground stopes create empty space. If a barrier fails, water follows gravity instantly and the system responds. We can mention this briefly and calmly because it underlines something gentle but true about the landscape around Silverton. This is not only a mineral district, it is a hydrologic district. Snowpack melts, water infiltrates fractures, Old workings connect parts of the subsurface. The mountain becomes a plumbing system, both natural and human-made, and that story continues quietly over time. Now we gently approach the modern endpoint of active mining at Sunnyside. By the later 20th century, mining in the Silverton area faced increasing economic pressures. Global competition, changing metal prices, and the high costs of operating in steep remote terrain all mattered. According to multiple accounts, the Sunnyside Mine was operated in the late 1980s and then closed in the year 1991, and its closure was a major event for Silverton because it represented the end of the last major mining operation in that immediate area at that time, with real impacts on jobs and on the local identity of the town. The closure story also connects to the environmental chapter, and it is important to handle that chapter with care. When mines close, the underground workings do not vanish. They remain as voids and tunnels that can collect and transmit water. In sulfide-rich districts, water interacting with sulfide minerals can become more acidic and can carry dissolved metals. Managing that water is difficult, especially in a landscape with many historic workings. Various reports and evaluations related to mine water in the region discuss how changes in drainage pathways and water management actions can influence where and how mine water emerges. It is not a simple story. It is a complex interaction between geology, old infrastructure, and hydrology. And it is part of why the Silverton region remains a focus of scientific and regulatory attention, even after major mining has ended. Now let us return to the specimen again, because we do not want the human story to pull us away from the rock. The rock is the calm centre of the whole video. Your specimen is a thin slice of quartz vein material with sphalerite and visible gold. In the language of the mine, it is the kind of ore that would have mattered not only for gold, but for the associated base metals and silver that often travel with sphalerite-bearing vein systems. In the language of the district, it is a piece of the structural corridor along the Eureka graben where faults and fractures created repeated pathways for mineralizing fluids. And in the language of history, it is the kind of ore that helped drive processing innovation, including the early adoption of selective flotation for lead and zinc ores. This is why I keep calling the specimen a window. It is not simply a pretty object. It is a compressed cross-section of a whole district narrative. Volcanic mountains fractured by caldera processes, hydrothermal fluids depositing quartz and sulfides, gold precipitating in fine grains, miners chasing those veins through steep terrain, and engineers developing methods to separate complex sulfide mixtures into usable products. From a collector's standpoint, the Sunnyside Mine name carries several kinds of weight. It carries geographic weight: San Juan County, Silverton area, high volcanic mountains. It carries geologic weight: epithermal to intermediate sulfidation style polymetallic veins in a caldera-related structural environment. It carries historical weight: a district that participated in the late 19th century mining boom, matured with rail access and processing infrastructure, and later became a site of major technological milestones and modern environmental complexity. And it carries aesthetic and educational weight: a combination of milky quartz, dark sulfide bands, and warm gold points that makes the ore readable. You do not need a microscope to appreciate that gold is present. You do not need to imagine the base metal component. Sphalerite is named and implied in the dark zones. The quartz provides the bright background that makes everything else stand out. If you wanted to compare this to other famous United States districts in a way that stays gentle, here is a simple framing. Some districts are famous because they produce specimens dominated by a single dramatic mineral habit, like large quartz crystals or spectacular wires of native silver. Some districts are famous for telluride minerals, where gold occurs in chemical combination with tellurium, producing minerals like calaverite and sylvanite. Some districts are famous for massive, metamorphic gold quartz veins, where the story is dominated by shear zones in ancient rocks. Sunnyside and the Eureka District sit in a different category: volcanic-hosted, structurally controlled, hydrothermal veins with a base metal suite that matters as much as the gold. The beauty is not only in crystals, it is in associations and textures. It is in the way the mineral system is layered and repeated. That is why a thin slice like this fits a sleepy format so well. You can look at it for a long time and always have something to notice, without needing dramatic changes. Your eye can drift across white quartz and rest. It can cross a darker band and rest. It can catch a gold speck and then let it go again. The specimen supports a calmer tension, the same way the mountains support long weathering cycles. Now, I want to bring everything together one last time, as a quiet closing loop, without repeating the same language you have already heard. This specimen began as a crack in volcanic rock, opened by stress in a complex caldera and fault environment. Hot fluids rose through the crack carrying silica and metals. Quartz deposited, sealing space, while pulses of sulfide deposition introduced minerals like sphalerite. At certain moments, the chemistry shifted enough for gold to precipitate as fine, visible grains, which became scattered points in the growing quartz framework. Much later, miners recognized these veins as sources of valuable metals and drove workings into the mountain to follow the mineralized structures. Over time, the district evolved from early high-grade shipping to a more mature industrial system supported by rail transport and advanced processing. In the early 20th century, processing breakthroughs like selective flotation helped make complex sulfide ores economically workable. In the later 20th century, renewed interest in gold and the study of visible gold in unoxidized ore added scientific depth to the mine story. And eventually, economic realities and the long challenges of water management in a historic mining landscape brought the major chapter of active mining to a close. All of that is contained quietly in a slice you can hold in your hand. If you're still awake, I want to thank you for spending this slow time with me on Sleepy Gold and Silver. If you enjoyed this 3-part deep dive, please like the video, subscribe to Sleepy Gold and Silver, and ring the notification bell. And if you want to leave a comment for future episodes, tell me what kind of specimen you want next. Another San Juan vein, a classic silver camp, a desert gold district, a telluride-rich piece, or something totally different like a skarn or a porphyry-related ore. For now, let the details fade softly. Let the image of milky quartz settle like snow. Let the dark sulfide bands become quiet shadows, and let the tiny gold points remain as a gentle reminder that even in hard rock formed under pressure and time there can be warmth.